Hello guys, welcome to the channel H2O, the A to Z of chemistry. All the students preparing for the JEE and the Neet examination and other competitive examination like NET and GATE, and all the students who do not like inorganic chemistry, well, we are preparing a complete playlist for you people called as Inorganic Made Easy. This is a playlist in which all the lectures you will be finding are put up in such a way that this is going to make the study of inorganic chemistry really very easy. And this playlist is also available in the Hindi voiceover too. So if you're comfortable in watching the same lecture in Hindi voiceover, you can just check the other playlist on our channel. Now, all these lectures, they are going to be very important for your examination. Many questions they are being repeatedly asked from the lectures that we are posting in this playlist. And all these lectures, they will be having some or the other trick, which is going to make the learning very easy for you people. So please do watch this complete playlist. This is going to be really very helpful for you to score more in the JEE and the NEET examination, and obviously the other ones too. Now, today's lecture, we will be talking about the trends for the thermal stability of ionic compounds. So this is going to be really very important. Frequently questions they are being asked, and well, remembering these trends for thermal stability, this becomes very difficult for the students, but I will be giving you just one simple trick and you will be learning all the trends for the ionic compounds. All right, so this is going to be, I hope, really helpful for you people. But before that, I will be giving you even the understanding what do we mean by thermal stability, what are the factors on which thermal stability they depend, so that you have a thorough understanding and then the trick to learn all the trends. I am Dr. Ritu Johar from the channel H2O, and I hope you will really enjoy your learning with me. So let us begin that. So first of all, let us understand what do we mean by thermal stability. So the ability of a chemical entity to withstand heat without breakdown, we call this as thermal stability, which means that if we have any chemical substance, we are heating it. Either it does not decompose or it is taking a lot of time, a lot of heat to be decomposing, then we call that compound to be thermally stable, stable to heat. All right, now we are talking about ionic compounds today. So let us look at the factors which are going to affect the thermal stability of ionic compounds. Now, ionic compounds, they are made up of what? They are made up of ions, a cation and an anion. So the factors which are going to be responsible for the thermal stability of the ionic compound. First of all, it is going to be the size of the ions. Smaller is going to be the size of the ion, greater will be the interactions, the forces between the different ions, and hence more stable the compound is going to be. For example, if you have to compare the thermal stability of sodium chloride and potassium chloride, so sodium ion, they are going to be smaller in size than the potassium ions. The chloride ions are going to be the same. So what we will be seeing is that the bonds in case of the sodium ion and the chloride ion in case of NaCl, they will be stronger than the bond between potassium ion and the chloride ions, and hence sodium chloride is going to be more stable than potassium chloride. Okay, now the next, what do we have? We have the charge on the ions. Higher is going to be the charge, higher is going to be the interionic attraction, and higher is going to be the stability of the ionic compound. For example, it's not been written down over here, but let us take the example of sodium chloride and magnesium chloride now. So magnesium chloride, magnesium is going to be +2 charge, sodium chloride, sodium is going to be +1 charge. In case of magnesium ion, the charge is more. So we will be finding that the interionic attractions are going to be more in case of magnesium chloride, and hence it is going to be thermally more stable than sodium chloride. Okay, now then therefore what we can conclude from this is that the thermal stability and the strength of the ionic bond is going to be inversely proportional to the size of the ion. Smaller will be the size, more will be the stability, because more is going to be the strength of the bond formed between the ions, and the strength and the thermal stability of the ionic compound is directly proportional to the charge on the ions. More will be the charge, more will be the strength, more will be the stability of the ionic compound. And from this, what we can conclude is that thermal stability of ionic compound is going to be directly proportional to lattice energy. Now, how do we conclude this? What is lattice energy? Let us quickly talk about lattice energy also. So when lattice energy, this is the energy that is going to be released when 1 mole of ionic solid is formed from its constituent ions in the gaseous phase, or the amount of energy required to break 1 mole of ionic solid or crystal into its constituent ions in the gaseous phase. So what this means is, for example, we have let us say sodium chloride. Okay, so we have Na ions and we have chlorine ions both in the gaseous phase. So we have oppositely charged ions in the gaseous phase. They are coming on close packing of these ions to form a crystalline solid. In this process, there is going to be energy that is going to be released, that is 787 kilojoule per mole. This energy is going to be called as lattice energy, amount of energy released when 1 mole of ionic solid is formed from the constituent ions in the gaseous phase. So we have the ions in the gaseous phase. They are on coming close to one another in a close packed structure, forming a crystalline solid, and hence energy is released, which is called as lattice energy. Or the other way around, what we can say is that there is going to be some energy which is going to be required to break the crystalline solid. That energy is also going to be called as lattice energy. Again, we have 1 mole of sodium chloride solid now. We are supplying the same amount of energy which was over here to break this into the constituent ions in the gaseous phase. This also is going to be called as lattice energy. Either to make the bond, how much energy is going to be released, or to break the bond, how much energy is required. This is called as lattice energy. And this lattice energy is given by U. The symbol for lattice energy, this is equal to K Q1 Q2 by R, where K is going to be a proportionality constant and lattice energy is going to be directly proportional to Q1 Q2, which are the charges on the ions. Q1 the charge on the cation and Q2 the charge on the anion, and which are separated by a distance R. Right? So now if the size is going to be more, the distance between the two ions is going to be more. So we can say the lattice energy is going to be inversely proportional to the size, and it is going to be directly proportional to the charge. Right? So higher is going to be the lattice energy, greater is going to be the attraction between the anion and the cation, and greater is going to be the stability of the ionic compound. Okay. So thermal stability of ionic compound, this is directly proportional to lattice energy. But please do remember one thing, that this is just one factor which we are saying as lattice energy, on which thermal stability depends. There are going to be other factors also, like the structure of the crystal. Okay, and there are going to be some other factors which we will not be talking about, but there are certain other factors also on which thermal stability it depends. But now what we are going to learn is the thermal stability of ionic compounds, the trends which are going to be important, which are frequently asked in the examination. So taking account all the factors on which thermal stability depends, I will be giving you just one trick, and with that trick, well, you will learn all the trends for thermal stability, and the best part is that there is going to be no exception to that trick also. Okay, so everything with just one trick we will be learning. So as we are going to talk about the trends now, first of all, we will be talking about the trends for the alkali metal salts, because the group 1 elements, they are going to be the largest in size in their periodic table in the respective periods, and hence they are the ones which can lose electrons very easily and form ionic compounds. And similarly, we will be talking about the trends for the ionic compounds made by the group 2 elements. Again, the alkaline earth metals, they also have low ionization enthalpies. They can also lose 2 electrons bonds easily to form ionic compounds. So these are the chiefly trends which are going to be asked to you in the examination. Now, as far as the thermal stability orders are concerned, now what is the trick? Well, the trick is friendship is between equals. If we have two children, they are going to be befriending each other. If they're going to be two adults, they will be befriending each other. But when it is going to be a small child and a large adult, well, the friendship between them is not going to be that strong. Similarly, if we talk about the friendship between a small cation, the small cation is going to be making friends with a small anion, and a large cation is going to be making friends with a large anion. In such a case, the thermal stability is going to be more. A small cation is going to be more stable with a small anion, and a large cation is going to be more stable with a large anion. And when I say a small anion, in case of now thermal stability, please do remember the small anions are going to be all monoatomic ions. What do I mean by monoatomic ions? We have the fluoride ion, the chloride ion, the bromide ion, the iodide ion, the oxide ion, the nitride ion. So all monoatomic ions, we will be considering them to be small anions for thermal stability, and the polyatomic anions, like we have the carbonate ion, we have the nitrate ion, the nitrite ion, the sulfate ion. So all these polyatomic, where the anion is going to be made up of more than one atoms, they are going to be all large anions. Okay, so small anion are monoatomic anions, and large anions, they are polyatomic ions. Just remember this, and then the small anion is going to be more stable with small cation, and large cation is going to be more stable with large anion, and your work is going to be done for the thermal stability orders. There is going to be one more trick that you will be learning when we will be talking about the solubility orders, which is also something similar only, but there will be some exceptions over there, some other things that you will have to remember. But as far as thermal stability is concerned, well, there is just one this trick and no exception to it. That is the beauty of this. Okay, so let us quickly see that. First of all, we have the oxides. So oxides, they are monoatomic, small anion, small cation is going to be more stable with it. So we will be finding that lithium oxide will be more stable. Down the group, stability is going to be decreasing because it will become a large cation with a small anion. Okay, next we move on to the hydrides. Again, H negative, monoatomic ion. So it is going to be more stable with the lithium ion, which is the smallest in the alkali metal series, right? So down the group, the stability of the hydrides is going to be decreasing. The next we have is the halide. It can be any halide now, right? It can be fluoride, chloride, bromide, iodide, anything. So all the halides down the group, the stability is going to be decreasing because they are monoatomic ions. Next we have is the hydroxide. So OH negative. So this is become a polyatomic ion now. So polyatomic ion, down the group, stability is going to increase. Large cation, large anion, stability is going to be the maximum. The next we have is the carbonates. Again, this is a large anion, polyatomic anion. So it is going to be more stable with a large cation. Down the group, stability is going to be increasing. The next we have is the bicarbonates. Again, the stability will be increasing down the group. Next we have is the nitrates. Again, polyatomic, large cation, large anion is going to be more stable. Down the group, stability is going to be increasing. The stability of the sulfates now. So down the group, again, the stability is going to be increasing. Again, peroxides. So peroxide ion O2 minus 2. So this is going to be again two oxygen atoms. So this is a polyatomic ion. So large anion, large cation is going to be more stable. Down the group, stability is going to be increasing. The next we have is the superoxides. So again, in the superoxides, what do we have? We have the ion to be O2 minus 1. So again, we have two oxygen atoms, polyatomic ion. So again, down the group, stability is going to be increasing. And next we have is the ozonide. So in the case of ozonide, it is O3 minus 1. Three oxygen atoms, again, large anion, down the group, stability is going to be increasing. Easy enough, I think. Just one trick and you remember all the thermal stability trends for the alkali metal salts. Now let us look at the alkaline earth metal salts. So again, the trick remains the same. For the thermal stability, friendship has to be between equals, small cation with small anion, large cation with large anion. Quickly seeing the trends, oxides now. So again, monoatomic oxide is going to be more stable with the smallest beryllium. Down the group, stability will be decreasing. Next we have is the halides. Again, all halogens, either it is fluoride, chloride, bromide or iodide, the stability is going to be decreasing down the group because the halides, they are going to be monoatomic. Okay. Next, nitride ion, this is N3 negative. Okay, so you are not going to see that here N2 is present. No, you have to see what is the ion. The ion is nitride ion. This is N minus 3. So this means this is a monoatomic ion. So it is going to be more stable with the beryllium atom. Down the group, stability is going to be decreasing. The next we have is the nitrates. So nitrate ion, so NO3 minus 1. So now this is polyatomic. So down the group, stability will be increasing. The next we have is the carbonates. Again polyatomic. Down the group, stability will be increasing. Then we have the sulfates. Again polyatomic. So down the group, stability is going to be increasing. Hydroxide, again OH minus 1. So again polyatomic. Down the group, stability is increasing. Then we have the oxalates. Again C2O4 minus 2. So again this is polyatomic in nature. Large anion, large cation is going to be more stable. So you can just do the orders for any of the salts. Just remember the small cation, small anion, large cation, large anion, and you know which is going to be more stable. So that would be all for this lecture. I hope now you're not going to make any mistake in case the thermal stability orders they are asked to you in the examination. And well, there are going to be more tricks, more concepts, more questions coming up. So please do subscribe to the channel. Click on the bell icon so that you get a notification the moment we put up the next lecture for you. And if you've liked this lecture, please do click on the like link and do share it with your friends. See you again. Have a nice day. God bless you.